Swayam Prabha. Digital India. Educated India.
Next, I am going to draw the bending moment diagram over here. Now, bending moment diagram, again from simple intuition, here it is going to be 0 because this is the free end. So and if I mark the points at A and B over here, so at M at A will be equals to 0. I have to find the M at B. So let's look at these relationships over here. So I know that dm dx equals to V, and in this particular case I have also written the expression for V over here. So that is minus q naught square by 2L, so which is degree 2, because we saw the shear is a quadratic. So that means that kind of tells you that your M will be cubic. Right? Okay, so now M is going to be cubic. Now I have found that my moment at A is 0 because A is a free end over here. So let me maybe go ahead and write that moment at A equals to 0. I'm going to have to find the moment at B. So how do I find that? I have this relationship that the difference in between the moments is the area of the shear force diagram between those 2 points. So I have my MB in this particular case, MB minus MA, right, is the area of the shear force diagram between this point and this one. Now there are 2 ways to do it. As you can see, it's a quadratic line. You can take this area that is there. Maybe let me mark it with green color. This area you can calculate as 1/3 of that rectangle of a circumscribing rectangle, because it's a parabolic thing with a 0 slope over here. Or you can simply integrate and find out. So what is going to be MB minus MA? I have the expression for the V over here. So it is going to be integral of 0 to L, a negative of q naught x square by 2L. So that will be L cube by 6. So eventually you will get as minus q naught L square by 6. Right? And I know that my MA is 0 over here. So MA goes 0. So this eventually gives you that your MB is minus q naught L square by 6. Right? So at A, at this point I have a 0 moment, and here I have a negative of q naught L square by 6. So let me go ahead and draw that vertical drop. So this is q naught L square by 6. Now here, although the value is 0, what is the slope? Again, go back to the relationships. It is going to tell you. So here the slope at x equals to 0 is equals to the value of the shear at x equals to 0, which is 0. So here again you have a 0 slope. So let's just mark that. So here you have a flat slope over here, and let's draw the shear. Let's draw the bending moment diagram. So it's a cubic line. So this is cubic. And here what is going to be the slope? Same, dm dx. I'm trying to calculate the slope at B will be equal to the V at B, which is equals to q naught L over 2. So here the slope is going to be q naught L over 2 at this particular point. It is the value of the shear at that particular point. Right? So, and also as you can say that your bending moment is negative and your shear force is also negative over here. So you have to do more number of problems to sort of get this into your DNA, that how the relationships are and how to use those relationships to get the values of the shear force and the bending moment. So let's compare this with what we got previously in the method of section. So you see how fast this was. We did not have to write an equation and so on. It was just using the relations we get it. This was our shear force quadratic q naught L over 2. This was cubic q naught L square over 6. And this is exactly what we have. So you have a quadratic relationship q naught L over 2 q naught L square by 6. Now in addition to what we had here before, now we could easily also compute these slopes at these different points that is there. So I hope this particular example was clear to you as well. Write down the problem in your notebook, try to do on your own, try to use the relationship and see that if you end up with the the same values here what we got or not. This is the next example problem where you have a triangular loading as you had before, but now it's a simply supported. Both the ends are simply supported. So we will see that how the the bending moment diagram and the shear force diagram varies. Now just from the looks of it, can you tell that whether the bending moment will be negative or positive? It will be positive because it's simply supported. It will be a hogging. It will be a sagging kind of a movement. So it will be positive. Sagging means that smiling. You remember that? Where is my one? So sagging is something like this. So it's a that smiley face, so it should be a positive one over here. Shear force we have to see. I'm not sure yet that how the shear force. I think there will be a negative part when you go from the left to right, but we'll see. So and just for the just so that we are used to seeing numbers and all, so instead of variables, let me just go ahead and put some numbers for you. I have some numbers over here, so I will write down the numbers. So let's say my q naught here is 2 kilonewton per meter. The length L is 4.5 meter. And please try this problem on your own and later you can come back and check. So your this Q becomes equals to 2 divided by 4.5 times X. Right? Is the linearly increasing load. So it is 0 at the left end and 2 at the right end, where you have that 4.5 load over here. Okay? And for here, for this one, I have calculated the reactions. So I will write the reactions over here. So I have my RA, which comes out as 1.5 kilonewton, and here I have my RB, which is 3 kilonewton. Now for this problem, unlike the previous ones, I haven't written out the relationships, so that slowly you get a hang of things and then you have it in your mind of what those relationships are. So we will directly jump into using those relationships over here. Right? So for here, let me go ahead and sort of mark the beams for where I'm going to draw the shear force and diagram and the bending moment diagram. So my shear force diagram I will draw on this beam over here, and I'm going to use this one for my bending moment diagram over here. Okay, so now jumping ahead for the shear force diagram, now always from the left to the right, from here to here you are going. So here at the end A, I don't have any option but to have a vertical of 1.5 because of this reaction which is over here. So let me go ahead and mark that vertical 1.5 over here. Right, now this is the vertical 1.5, and how is the variation going to be? Let's look at the relationships. We know that our dv dx, just recollect the relationships which we have, is minus of w as a function of x, which in this particular case is minus of 2x divided by 4.5, so which is degree 1. So that tells you that your v is going to be a degree 2. So v is going to be quadratic. So you have a quadratic variation from A to B. Why? Because this linearly increasing load spans that entire beam. So throughout you're going to have a quadratic relationship. Now a couple of things. So let's just calculate the V at B, because I already know the V at A at 1.5. So we know that my VB minus VA is what? Is the negative of the area of loading between B and A. So in this case is going to be VB minus VA. I know I have already computed, which is 1.5 minus 1.5 will be negative of this loading. So this is the length is 4.5 and this height over here is 2. So minus of half times 4.5 times 2, which is equals to minus of 4.5. And as you can tell that your VB is going to be minus 3 kilonewton, which is quite obvious as well. I did not need to do that because I know here it's 3, it is going up. So over here, so here I'm going to have a negative 3 at the right end. So I'm going to draw that. I'm drawing on the lower half plane, so I don't need to mark it as a negative sign. So this is going to be 3. And what is the radiation from A? So let me mark those points as well. So this is my point A and this is my point B. So from your A to B, the variation is a quadratic variation. So let me just go ahead and draw that. And also, what is the slope at A? The slope at A is going to be the dv dx at x equals to A, which is 2 times 0, because x equals to 0 at A. You can tell from the loading diagram as well. So the value of the slope at A, the value of the slope of the shear at A is going to be the value of the distributed load at A. So that is 0 over here. So you are going to have 0 slope over here, whereas here at 3 you are going to have a slope of minus 2, because it's minus of W at X at B. So that is equals to minus 2 over here. You're going to have a minus 2. So let me just draw the quadratic shear force diagram and then I will mark the slope. So this is how my shear varies. So here at the right end I have this particular slope that is there. So here let me mark it. So this is slope equals to 0, and here my slope is negative 2. Okay, so now as you can see that here I have a positive part and a negative part over here. Now the question is, where does this happen? Where does the v equals to 0? So I don't know, I'll maybe mark this point as C over here. So the question is, what is this XC, where XC is this distance from the left end to this right end over here. So what is this XC? How do we compute XC? Pretty easy, pretty straightforward. I know the shear at A is 1.5. I know the shear at C is 0. So I'm again going to use this kind of a relationship which I had over here, similar kind of a relationship. I'm going to write it again. So I'm trying to find what is my XC. So I have my VC minus VA is going to be the area of the loading diagram between C and A. So C may be happening somewhere over here. So the area of the loading diagram. So here, remember what I have marked XC over here, it is maybe somewhat similar to your this particular point. So this is my XC, right? So the area of the loading diagram from here to here is going to be this part, this part over here. So this is going to be equals to half base times the altitude that you get, that is 2xc by 4.5, because the load is a linear function of x that you have. Now here I already know the value of VA. So the value of VA is 1.5 over here, right? And the value of VC is 0. So, oh sorry, I missed a negative sign, because VC minus VA is the negative of the area of the loading diagram, right? So it is I have a negative sign over here. Before that I have a negative. Let me erase that and write it properly. I have a prominent negative sign over here. So I have that XC square divided by 4.5 is equal to 1.5. So that gives you a value of XC. So let's calculate that. That is going to be 4.5 times 1.5 and the square root of that one, that is 2.6. So XC is 2.6 meters. So that gives you the point at which the shear is becoming 0. So this XC, which we found out over here, XC comes out as equals to 2.6 meters. Now So our shear force diagram is done. So this is my shear force diagram, SFD, which we just do over here. Now the next is the bending moment diagram. So for the bending moment diagram, again, let's use our intuition of what we have, that at this particular point, so before you start solving, before you start writing, always use your intuition to lessen your hassle. Essentially, that what does this intuitively tell you? You have the left end, you have a pin, you have the right end, you have a roller. So that means, and there is no concentrated moment, so the moment at A and the moment at B must be equal to the 0 over here. So we know, let me draw a divider line over here and write that out, that moment at A must be equals to 0, moment at B must be equals to 0. And how is the variation going to be? Since my V is degree 2, that tells me, since my dm dx equals to V, so that tells you that your moment must be cubic, right? We have a cubic variation from A all the way to B. So this is your A and this is your B. You have a cubic variation, and at A the value of the moment is 0, at B the value of the moment is also 0, right? And also, can you guess that where the maximum is going to happen, maximum moment? Yes, you're right, the maximum is going to happen where the shear is 0, because from this relationship, where the shear equals to 0, the maxima you are going to get at that particular point, right? So you have a maximum at, so let's just maybe mark the ordinate as well, just so that it serves as a good guideline while we are drawing these problems. Let's see, I'm going to just drop this line over here. So how is the moment is going to vary? It is going to have a maximum at C, 0 at A, and the 0 at B, using a cubic variation that you have. So the variation is going to be somewhat like this. So you will have a 0 slope here. At this particular point, you will have a 0 slope. And can you guess that what is the slope going to be at this particular point at A? So the slope will be equal to, you remember that this relationship, that the slope at A at this particular point will be the value of the shear at A, which is equals to 1.5, the value of the shear at here at 1.5. So here the slope is 1.5, here the slope is 0, because that is the maximum point. And then again, you can maybe mark the slope at the point B here. So here the slope is -3, because the value of the shear force at B. So here the slope So see how easily we derived this shear force diagram and the bending moment diagram, and the shear force is completely positive over here, because you're going from 0 to a 0 and you're starting with a positive slope, meeting a slope of 0 in between, and then you're going down. Now the one question which remains is that what is the value of the maximum M max? So that also you can easily calculate. So using similarly what we did for the shear to calculate essentially XC, we know where XC is now. What we have to find is M max. So M max happens at this point C over here. So M max equals to MC. So how do we get this? We get this, your MC minus MA is the area of the loading diagram, of the area of the shear diagram. So the moment is related to the shear. So the MC minus MA is the area of the shear force diagram between C and A, right? So that you can substitute here, take the expression for the moment, take the expression for the shear that you have, and you calculate. I'm not going to do the integration. You will know how to do that, or otherwise you can since this is a varies something like this, you can calculate that by integration, and what it will come out as, I have the value here already, so I'm going to write that. So M max here comes out as equals to 2.6 kilonewton meter. So calculate that and check whether you get the same result here or not. So I hope that this example was also clear. We had a simply supported beam with a a triangular loading, and from that we derive the shear force diagram and the bending moment diagram. So let us now look at another application example for the shear force diagram and the bending moment diagram, where you have a part triangular load. So you have a cantilever beam which is clamped at this support C. You have a triangular load which goes from W0 to here, and at certain distance A it drops down to 0, but it's a linear variation, and the total length of the beam is L. So how do we go about solving this? So see here, this is a problem where method of sections can be quite nightmarish, because suppose if you take a a section somewhere here, or a section somewhere here, right? Suppose if you're going from left to right, then you have to, if you're taking a section here, you have to deal with a trapezoidal kind of a loading if you want to avoid having many loads such as the reactions and so on. Or say if you're starting from here, then you have to compute the reactions, the vertical reaction and the moment, and then go from here to here, take one section and then take another section here. So you will see in this is one example where you truly start to see the merit of using the relationships to draw the bending moment diagram and the shear force diagram. So let's go ahead and try to do this problem. So I have drawn two beams below here. One is for the shear force diagram, one is for the bending moment diagram over here. So let's first start with the shear force diagram. So here, see, just by looking at the problem, you see at the very end over here there is no concentrated load, so your shear force at that particular point is going to be 0. So this is my SFD, and just for convenience of drawing, let me draw the lines that we have, right? The guidelines. So of course this is my point A. Intermediate, I have where the triangular load ends, I have the point B, because those are the places. The reason for drawing the guidelines is that those are the places we expect transitions to happen. So just for a neater diagram, it is often convenient to draw this guideline. All right, so now that we have the guidelines, let's for the first beam, let's mark the points as well. So this is my A, here is my B, and here is my C. Now, as we hypothesized, at this particular point, my shear force will be 0. So at this particular point, I will have no shear. Right? Now, let's see how the shear force diagram varies. So let's write down our expression again. So we have our dV in dx is minus of w, which is a function of x that we have over here. This is the general form of the equation, and so that kind of tells you that here our w is in this particular problem, this w is a degree 1, because it's a linearly decreasing load. So that again tells you that your v must be second degree, that is, it must be quadratic. So you will have, as long as the load is present, where the load is present from A to B, you will have a quadratic variation of the shear force diagram. Now, how is the quadratic variation going to happen? We know that it is 0 over here, and what is going to be the value of the shear at this point B? We can find that out as well. So we have VB minus VA will be negative of the area of, this is again the relationships which we had looked at, loading diagram, which is in this case nothing but, what is the area of the loading diagram? It is half times A times W0 over here, half times base times altitude. So minus W0 A divided by 2. So I know that here the shear force is 0, and at this particular point, somewhere at the point B, I have the value over here is W0 A divided by 2. And at that particular point, I have not put the negative sign because I'm drawing in the lower half plane. And also, so from A to B, that is from the shear force